Hello, and welcome to another lesson for Math 1106, Math for Business Precalculus. My name is John Adamski. This is week 9. We're going to continue our study of functions by studying the composition of functions. Now, when I say we've been studying functions, we definitely know how to plug numbers into functions. We know how, in general, to determine what numbers we can plug into functions. That is to say, we know how to find the domain of functions. We know how to study functions and read information about functions using their graphs. That was last week's lesson. And now, the main skill we want to develop today is the ability to plug expressions into functions. That's the main thing. Everything else is really just that, plugging expressions into functions. And that will test our algebraic skills and our ability to follow the order of operations and things like that. Once we get that skill down, we'll define what it means to compose two functions. We'll talk about function composition, and we'll talk specifically about one example of all of this involving difference quotients. When you get to a calculus class, one of the first things you're going to need to do is simplify difference quotients. And this will depend on this skill that we're going to develop today of being able to plug expressions into functions and compute the result correctly. Okay? So let's get to it. The key is to understand what a function really is. A function is really a set of instructions on how to take input and turn it into output. Okay? Sometimes it's visualized as this like mysterious black box. Something goes in, something happens to that thing, and something comes out. Okay? Input is turned into output by following instructions. So think of a function as the verb. It's defined by what it does. When I look at f of x equals x squared, the function f has nothing to do with x. Okay? In fact, I could define the exact same function with a different symbol. I could turn this into a w and say f of w is w squared. What this is telling me is that what this function does to input, you can call it whatever you want, is it squares the input. That's how it produces the output. So no matter what goes in, and you can be really cute, you can put any kind of symbol here that you want. The point is that what comes out of this function is the square of what went into it. Okay? We usually do put x here, so I do want you to get familiar with seeing it as x. But there's nothing special about x in this definition. It's just what's called a dummy variable. It could be interchangeable with any other symbol. It's just telling you that whatever the input is, square that, and that's how you get the output. So for example, if a is the input, f of a would be a squared. OK, that's pretty easy. F of 2a. If 2a goes in, what comes out? Well, we need to square the input. What is the input? The input is 2a. So we need to square 2a. Now, the parentheses actually are important here because I want to treat 2a as if it's one number. It looks like it's the product of two numbers. It looks like it's two separate numbers multiplied together. It is, but I want to treat it like one number. 2a squared, that's literally 2a times 2a. We know that that's 4a squared. I could have gotten that also by just squaring the 2 and squaring the a. So the point here is that oftentimes parentheses are really important. Had I not put the parentheses down there and just written 2a squared, that is not the same thing as 4a squared. The 2 is not being squared. The 2 needed to be squared. The 2 was part of the input. Okay? So I have some tips here for how to correctly evaluate the output of a function when the input is an expression. And the very first thing I would like to do is replace x with parentheses. What I mean by that is, I'll come back, I'll put this right back there. But when I see the function f of x equals x squared, I would like to replace everything, all the x's on the right-hand side with open parentheses. So I'm saying f of the input is the input squared. This is a nice setup. This is the setup that I advise you to do at least the first few times that you are practicing this. Set yourself up with this sort of template, okay? With open parentheses in place of the x's. Now, what do you want to input into this function? Well, I had written 2a minus 3b. So that's the input. And I need to, this function takes the input and squares it. Now the parentheses are very important here. Once I write this down, the rest is probably pretty easy, okay? It's the setup that is the new part. The rest should be review. This means 2a minus 3b times 2a minus 3b. Don't you dare just square the 2a and square the 3b. You'd be missing out on some of the multiplications. There's actually 4 multiplications. 4a squared minus 6ab minus 6ab again plus 9b squared. And generally, you know, I want to combine similar terms, so I would call this 4a squared minus 12ab plus 9b squared. Okay? And this is how you plug an expression into a function. All right, so let's get some more practice plugging expressions into functions. If my function f is this quadratic function, 2x squared plus 4x plus 1, what this is telling me is it's telling me the instructions that this function follows to produce output. Whatever the input happens to be, it's going to take the input. We're referring to it as x for the moment, but we could refer to it as anything. We take the input and we square it. Then we double that and add it to 4 times the input plus 1. Okay? That's a set of instructions. And the way I read it as the input squared times 2 plus 4 times the input plus 1 is important. Instead of saying x, I'm saying the input. Because in this setting, x just represents the input. Now down here I say find f of x plus 1. Now a typical thing that people do, that students do for the first time, is they say, oh, well this is f of x plus 1. Now I get it. That is how I read this. This is f of x plus 1, and here you have f of x plus 1. But that's not what's going on here, okay? That's not how you do this at all. What we do is we understand, okay, so you're plugging something into the function. Let me go ahead and give myself that template that I mentioned before, okay? Replace x with open parentheses. So I'm just going to copy this line down as this, 2 times the input squared plus 4 times the input plus 1. That's a great template. Now, what do you want to plug into f? I believe I had an x plus 1 here. That's what I want to plug into f. What do? Inside every one of these open parentheses, I put an x plus 1. And that's it, okay? If you get this far, you're most of the way there. Now just take it home. We're going to follow the order of operations. We're going to first square this. We do exponents first. So this is going to be 2 times. We got x squared plus 2x plus 1. Plus, I'll just copy down the rest, 4 times x plus 1 plus 1. Now we're going to distribute. We're going to distribute that 2 and this 4. So we're going to get 2x squared plus 4x plus 2. Over here, we're going to get 4x plus 4 plus 1. And lastly, I'm just going to combine my similar terms. So I see only one x squared term. So I get 2x squared. I have a couple x terms. I have a 4x here and a 4x here. That's 8x. And I have a 2 here. That's a constant term. Another constant of 2 here. That's 6 so far. Plus 1 makes 7. So plus 7. OK? So what is f of x plus 1? It's 2x squared plus 8x plus 7. This is how you do it. What if I gave you a fraction like this? What if I want to know what is f of 1 over x? Well, I hope you're catching on that it's really not that big of a deal. Whatever you're going to input into f, you are going to square it, then multiply it by 2, and then add 4 times the input plus 1. This is the template that I'm recommending here, replacing all of the x's with open parentheses. Now put the input in all the parentheses. What do you want to input into the function? We said 1 over x. So a 1 over x goes in all of these open parentheses. Okay, this is the setup. Now you just have to evaluate it. Okay, so what does this produce? What output does this produce? Well, this will be 2 times. The rule for exponents says to square the top, square the bottom. We're going to get 1 over x squared plus 4 times 1 over x. I'll just leave it as 4 times 1 over x plus 1. Okay, so what do I have here? This is 2 times 1 over x squared. That's 2 over x squared plus 4 over x plus 1. I could leave it like this, but let's go ahead and get common denominators. Okay? The denominators that I see are x and x squared. The least common denominator would be x squared, x raised to the highest power that I see. So this one already has the denominator x squared. I can make this one have the denominator x squared by multiplying it by x over x. And I can make this one have the denominator x squared by multiplying it by x squared over x squared. Now I've got 2 over x squared plus 4x over x squared plus x squared over x squared. And since they all have the same denominator, I can write that as one fraction with x squared in the denominator. And the numerator is 2 plus 4x plus x squared. Okay, that would be my final answer. Okay, one more example for good measure. I want to know, given several different functions, can you evaluate f of x plus h? In a calculus course, being able to plug x plus h into a function is something you're going to have to do. Okay, so let's make sure we can do it. If the function f is 5x squared, what's f of x plus h? Well, again, a common mistake would be to say that f of x plus h is f of x plus h. That is incorrect. Okay? The correct thing to do, and I still have the tips on the board, the correct thing to do is to set yourself up for success by rewriting this, giving yourself a proper template for what this function does to any input. No matter what the input is, you should square it and then multiply it by 5. That's what this says. When we say f of x equals 5x squared, this is what it means. The function is more about the verb, what it does, than the particular way that it looks. Okay? So what is f of x plus h? F of x plus h is 5 times x plus h squared. If you can get this far, you can get it all the way. So I'll just follow the order of operations. This is going to be 5 times. Now, when you multiply x plus h times x plus h, you get x squared plus 2xh plus h squared. And when you distribute that 5 to all 3 terms, you get your final answer of 5x squared plus 10xh plus 5h squared. That's the final answer. We're done. What if the function was this? What if it was the square root of 1 minus 2x? Okay, that is to say that this function is the square root of 1 minus 2 times the input. Okay, no matter what the input is, this is what it does to it to produce the output. And if you wanted to input x plus h, as we do, then we're just going to put x plus h inside of all of these parentheses. And now we're just going to simplify it as much as possible. In this particular case, there's not a whole heck of a lot to do, except we can take this negative 2 and distribute it to the terms inside parentheses to produce the square root of 1 minus 2x minus 2h. That's all I can do. Okay? You cannot, by the way, take the square root of 1, subtract the square root of 2x, subtract the square root of 2h. The square root is not a linear operator in that way. You cannot distribute the square root among those terms. Okay? There's no such rule for that. My last example over here, suppose f of x is a rational function, okay? A ratio of polynomials or a fraction. The rules are not any different. Okay? I understand that this function, what it does is it takes the input, whatever it is, it will take the input and add 2, then divide by 3 minus the input. Okay? The parentheses are very important. In all of these cases, the parentheses are doing things. Here, if you want to know what is f of x plus h, I'll set myself up like this. Okay? And the parentheses are important, not so much in the top. The top is x plus h plus 2, and that's the same with or without the parentheses. But downstairs, they are doing something. I'm supposed to subtract the x and subtract the h. That's a 3 minus x minus h. Okay? So some of these parentheses that you put down in this template won't be needed in the end, but they're not causing any problems. Other parentheses are crucial, and without them, you will get the wrong answer. So I'm saying just always replace the x's with open parentheses, and you can't go wrong. OK, so we've been playing around with this idea that functions are instructions that say how to take input and turn it into output. This idea of input and output is at the crux of the idea of functions. Now, if I have two functions, let's call one of them f and one of them g. One thing I could do is plug something into g and get something out. If I call the input x, then I'll call the output g of x. Totally fine. But I have two functions. So what I want to do with my next function is I want to line it up so that whatever comes out of g, the output of g, becomes the input of f. And so if g of x goes into f, what comes out of f? Well, f of its input. In this case, the input was g of x. So what comes out of f is f of g of x. Okay? This is what it means to compose two functions. It's to form a chain of functions linked together in this way where the output of one function becomes the input into the next function. And you could continue this. You could line up a third function so that the output of f becomes the input of a third function, and so forth. Okay? When you reach calculus, you'll learn something called the chain rule, and it is going to show you how to find derivatives of functions that are composed like this. So keep the idea of these things being linked together to form a chain of functions in the back of your mind somewhere. Now, instead of writing f of g of x, like we are here, you can also notate it another way, and you'll see this in your textbooks from time to time, f of g of x. It's read the same as this, f of g of x. This is read f of g of x same way. Okay, and it means the exact same thing. So let's look at an example. I give you two functions. F of x is 3x plus 5. G of x is x squared minus 1. What's f of g of x? Okay, let's see. Well, first of all, I'm going to say this is f of g of x. Cool. That's by definition what that set of symbols on the left means. Now, that means we're going to have to plug something into f. Okay? If whenever you plug something into f, let's get rid of this. Ultimately, this is f of something. What does f do? F multiplies its input by 3, and then it adds 5. So I want to know what is f of g of x. OK, well, that'll be 3 times g of x plus 5. OK, what is that? Well, g of x is x squared minus 1. Aha. So this is 3 times x squared minus 1 plus 5. And all I have to do is distribute that 3. See how the parentheses are necessary? I get 3x squared minus 3 plus 5. Or we'll just call that 3x squared plus 2. OK, combining the 5 and the negative 3 to be a 2. That's it. All right, let's try it again. Here I've got g of f of x. All right, well, that's g of something. It's g of f of x. Maybe this time I'll just take care of this right away. That's g of, what is f of x? F of x is 3x plus 5. So we're plugging 3x plus 5 into g. We've already done stuff like this, OK? That's why I started with plugging expressions into functions. I didn't use the words of function composition, but that's what we were doing. We know how to plug this expression into g. What do? Well, this is g of something, correct? And g of whatever it is, g is the input squared minus 1. So we're going to get the input squared minus 1. What's going into g is 3x plus 5. So we have 3x plus 5 squared minus 1. When I square this, I'll get 9x squared plus 30x. That's 2 times 5 times 3x plus 25 minus 1. Well, the 25 minus 1, let's call that 24. And that's it. Okay? Let's try it with this, f of x. This is interesting. You're going to put x into f. I'll write it out. You're going to plug x into f. Something's going to be output by f. And you're going to take that output of f and make it the input into f. Okay? So what is this? This is f of 3x plus 5. Okay? Well, what does f do? F is 3 times its input plus 5. Right? That's what f is. F of input is 3 times input plus 5. This is f of something, so it's 3 times something plus 5. F of what? F of 3x plus 5. Okay? So do you see how here's f, but on the outside is also f. This is f of x. And now you just have to evaluate what this is. So there's some distributions to take care of. I'm going to get 9x plus 15 plus 5. We'll call that 9x plus 20. Okay, and that's my final answer there. Let's do the same thing with g. Let's figure out g of x. So first thing I do is write this out as g of x. That's g of something. It happens to be g of x squared minus 1. Okay? Now g of anything is g of the input is the input squared minus 1. In this case, the input is x squared minus 1. All right? So we've set ourselves up. Now the rest is just how do you evaluate this? Well, by following the order of operations. I'm going to square the x squared minus 1. That involves foiling. That's going to give me an x to the 4th minus 2x squared plus 1 minus 1. And the plus 1 minus 1 cancel. So my final answer is just x to the 4th minus 2x squared. And that's it. Now, in last week's lesson, we were talking about secant lines. A secant line is any line that connects 2 points on a graph. So say I've got the graph of a function, y equals f of x. And I've got 2 points on that graph. I can connect them with a line, and I can talk about the slope of that line. OK, that's all I want to do. But I want to specify the coordinates of these points in a kind of funny way. I want to be very vague. I want to say that this is the first point, and its x coordinate is just x. OK? Well, I'm showing you that, and I've labeled this point with the x coordinate x. Now, since it's on the graph where y equals f of x, I know that the y coordinate must be f of x. OK? And the other point, instead of giving it a number or another letter, I'm going to call it x plus h. In other words, if this is x, add h to that number, and now you're at x plus h. OK, this is the second point, and its x coordinate is x plus h. Its y coordinate is f of x plus h, because it's on the graph where y coordinates are f of the x coordinates. And I want to compute the slope of this secant line. OK? This is what it's going to be. It's going to be the change in y, the difference of these two y coordinates, so f of x plus h minus f of x, divided by the difference of their x coordinates. That's x plus h minus x, which is just h. H is the horizontal distance between these 2 points. Okay? So this is just the formula for slope. It's the slope connecting these 2 points. It's the slope of the secant line. We also learned last week this is called the average rate of change of your function f over the interval from x to x plus h. However you want to call it, this is what I'm talking about. And it actually goes by a third name. It's called a difference quotient, because you've got a difference of y coordinates and a difference of x coordinates, and you're taking the quotient. Okay? So sometimes it's called a difference quotient. And what I want to do is simplify the difference quotient for different functions. Okay? The first one I want to look at is this one, this quadratic, x squared minus 6x minus 2. So what I'm trying to compute is I'm trying to compute f of x plus h minus f of x divided by h. Okay? And first, let's see. I'm going to have to plug x plus h into my function f. Well, I know how to do that. F is this function that takes its input and squares it, subtracts 6 times its input, and then subtracts 2. That's what f of x plus h is. Or that's what f does to any input. To x plus h, it will give me x plus h squared minus 6 times x plus h minus 2. OK, so that takes care of f of x plus h. Then I want to subtract f of x. So I want to subtract something. Now, I want to subtract all of f of x. F of x has 3 terms in it, and I need to subtract all of them. Okay, so what I need here is something that can group these 3 terms together to be one thing f of x. So I'm going to subtract x squared minus 6x minus 2. Those parentheses are important. All of this is being divided by h. Okay? Now, with that, if you've gotten this far, I think you can finish the rest of this. Okay? We just have to follow the order of operations and stay calm. So when I square x plus h, I get x squared plus 2xh plus h squared. That involves foiling it out. Then I'm going to subtract 6x and subtract 6h. So I have minus 6x minus 6h, and there's still a minus 2 at the end. Okay? Then I need to subtract the x squared, subtract the negative 6x, which is to say add 6x, and subtract the negative 2, which is to say add 2. That's my numerator. And the denominator, of course, is just h. Now, do stay calm, because while this is getting pretty ugly, it's going to get very pretty in the end. Notice already that there are some cancellations. There's a x squared here and a negative x squared over here. Those add up to 0, so I'm just going to cross them out. I've got a positive 6x here, and I've got a negative 6x here. Those add up to 0 also. And this negative 2 here and this positive 2 here add up to 0. Okay? Difference quotients are going to result in cancellations like this. And if we clean up what's left, what is left? I have a 2xh plus h squared minus 6h. And that's it. There's only 3 terms upstairs that haven't gone away. And there's still an h downstairs. Okay? It's cleaned up pretty well. It can get even nicer. So what I want to do is factor. In the numerator, every single term upstairs has a factor of h. I can pull out a factor of h, and it will leave behind a 2x plus h minus 6. And that's being divided by h. Okay? And here's the payoff for taking the time to factor that out. That h and this h cancel. So in the end, this cleans up very nicely. My simplified difference quotient is just 2x plus h minus 6. That's it. Let's do it again. Let's find and simplify this difference quotient, where f is now a square root function, the square root of 1 minus x. Okay? The setup is sort of the same. You're looking at what I need to do. I need to input x plus h into f. Well, what is f? F is the square root of 1 minus its input. For this, the input is x plus h. So we're going to put an x plus h here. Okay? So what I've got right here is f of x plus h. Cool. At some point, I'm going to distribute that negative sign, but maybe I'll leave that for another time. Then I need to subtract f of x, so I need to subtract the square root of 1 minus x. Cool. And all of this is being divided by h. All right, that's the setup. Like I said, I guess I could distribute this negative sign. Maybe let's just do that right now. We're going to subtract x, subtract h, So we're going to get minus x minus h underneath the square root sign. Minus x minus h. All right, well, what else can I do? I found this, but I'm supposed to simplify it. When those are the directions, that's a hint that you should try some stuff that this can be cleaned up. And we've seen things like this before. We've looked at how to rationalize a numerator. Okay? We know that if you multiply something minus something else, and I've got something minus something else right here, okay? What we know for sure, what we've seen before, is that if you multiply a minus b, the difference of two things, if you were to multiply them by the sum of those same two things, if you were to multiply this by a plus b, okay? What's a minus b times a plus b? Well, it's a squared minus b squared, correct? Maybe I'll continue the color. It's a squared minus b squared. So it would result in squaring this and squaring that, and that would get rid of the square roots. Okay? So what would that look like? Well, that would look like multiplying this by the square root of 1 minus x minus h plus the square root of 1 minus x. Okay? And as long as you do that downstairs as well, that's actually a legal move. Whenever I multiply a fraction by something divided by the exact same thing, this fraction right here is 1, correct? Its numerator and denominator are exactly the same. So that fraction right here is 1. Okay? I'm choosing to multiply this expression by this because I see the pattern. I see what's going to happen. When you have the difference of two things times the sum of those same two things, the result is the first thing squared minus the second thing squared. And so for us, the first thing is going to, that means you're going to have 1 minus x minus h square root squared minus the square root of 1 minus x, the second thing, squared. Okay? And downstairs, it's going to be a little ugly. It's going to be h times the square root of 1 minus x minus h plus the square root of 1 minus x. Okay? It's just this denominator times this denominator. And I'm not going to bother distributing this because I know where this is going. Okay? Now, there's an obvious cancellation here. Of course, when you're taking the square root of something and then you're squaring it, you can just get rid of those things. Okay? And over here, you can do the same thing, but be careful. Right now, the 1 minus x is being grouped together. It's all underneath a square root sign, and it's all being squared. But when I make this cancellation, those grouping things go away. I need to put parentheses around this. I was supposed to subtract all of this. And when I get rid of the square root and the squaring, I'm going to need something to contain them to treat this as one thing. I need parentheses. So where are we now? Well, let's see. What we have upstairs is 1 minus x minus h. And then we have a minus 1 minus x. Downstairs, we have still just h times the square root of 1 minus x minus h plus the square root of 1 minus x. Now, there's a lot of cancellations to be made here, okay? I won't take the time to write out what this looks like when I distribute the minus sign, but you see that there is a minus 1 here, and there's a plus 1 there. So we have a 1 minus 1. Those cancel. We also have a negative x minus a negative x. That's negative x plus x. Those combine to be 0 as well. Okay? So the only thing that's upstairs is a negative h. I will write this out to make this clear. You have negative h upstairs, and downstairs you have h times the square root of 1 minus x minus h plus the square root of 1 minus x. Okay? And we're in the home stretch. It should be clear what to do now to finish this up. I want to cancel that h upstairs with this h downstairs, and that's my final answer. When I cancel that h upstairs it leaves behind a negative 1. So my final answer is negative 1 over the square root of 1 minus x minus h plus the square root of 1 minus x. And that's my final answer. That's my simplified difference quotient. Okay, and let's wrap this lesson up with one last example. I want to simplify a difference quotient for the function f of x equals 3 over 2 minus x. Now I've got a fraction. I've got some variables in the denominator, and I just want to show you how this works in that case. Okay? Now, in this setting, instead of writing the following, when I set this up, of course, I could write it this way. I could say that it's 3 over 2 minus x plus h minus 3 over 2 minus x all over h. But I don't like to have compound fractions. I don't like to have fractions inside of my fraction if I can avoid it. So instead of setting it up like that, let me just acknowledge that ultimately we're going to have this minus this, and it's going to be divided by h. Now, to divide by h is the same as to multiply by 1 over h. So I'm going to write this out like this. I'm going to say this is 1 over h times f of x plus h minus f of x. Okay? I'll just write it, f of x plus h minus f of x. Okay? That's just how I like to write this. So that's 1 over h times f of x plus h. That's going to be 3 divided by 2 minus the input. Here the input is x plus h. So inside this parentheses goes x plus h. And I subtract f of x, which is 3 over 2 minus x. All right, that's the setup. If you can get this far, you're halfway there. The rest is just simplifying this as much as possible. Okay? And in this case, I want to actually get common denominators. I want to add these fractions together. So let's see. What do I have here? I have 1 over h times, and this fraction, of course, is 3 divided by, let's distribute that negative sign. So I have 2 minus x minus h. Okay? And over here, I'm subtracting 3 divided by 2 minus x. Now, in this case, close parentheses. Okay? Now, the LCD, if you're gonna add these fractions together, you have to write them with the same denominator. Okay? And you have to be able to know what that least common denominator is going to be. Now, the least common denominator needs to be a multiple of this denominator. It needs to be a multiple of 2 minus x minus h. It also needs to be a multiple of this denominator, 2 minus x. And since 2 minus x minus h and 2 minus x don't have any common factors, that means that the LCD is going to be the product of those two denominators. Okay? So I have to make that the new denominator for both fractions. And the way to do that is to take this fraction and multiply it by, well, it already has the 2 minus x minus h. What that denominator is missing is the 2 minus x. So we're going to multiply it by 2 minus x. We're also going to multiply the numerator by 2 minus x so that we're not actually changing the value of the fraction. And over here, we're going to do something similar. This denominator already has the 2 minus x. What it needs is the 2 minus x minus h. We will multiply this denominator by 2 minus x minus h. And we're going to do the same thing upstairs, too, so that this is a legal move. Okay? Now we have common denominators. And in fact, let's just see what I have. I have 1 over h times, and now I'm going to write this as a single fraction because both of these fractions have the same denominator. That denominator is 2 minus x minus h times 2 minus x. And what is the numerator? Well, the numerator is 3 times 2 minus x. That's a 6 minus 3x. 6 minus 3x. And then we're subtracting something. Okay, we're subtracting all of this. What is all of this? Well, we have 3 times 2, that's 6. 3 times negative x, that's a negative 3x. And a 3 times negative h, that's a negative 3h. Okay? All right, that's where I'm at. Maybe you can see that there are some cancellations. For example, there's a 6 minus 6. Those 6's cancel. There is a negative 3x minus a negative 3x. Those also cancel. In fact, your numerator is 1 times negative 3h. That's a positive 3h. What we're left with here is a single fraction where the numerator is just 3h. And what's the denominator? Well, it's h times 2 minus x minus h times 2 minus x. And maybe you see the final move here. The final move is to cancel this h and this h, and that leaves you with your final answer. Just to write it out, that would be 3 divided by 2 minus x minus h times 2 minus x. Okay? So be careful. In all of these examples, I never did any distribution in the denominator. Okay? I never distributed the 2 minus x minus h. I never did all of that. That would have messed this all up. It was very nice to always have the denominator in its factored form, because you may have noticed in all of these examples that h that I started out with in the denominator, it eventually goes away. So if you had distributed that h out, you wouldn't have been able to nicely make the cancellation in the end. So a little tip is do not perform any distribution in the denominators of your difference quotient so that you can make the cancellations and simplify nicely in the end. Anyway, that's my final answer, and that was my last example. That's it.